We'll now look into a couple of more different probability rules. And in order to do this, we're going to start with the definition. And that's the definition of independent events. We say two events are independent if the fact that the first one occurs, the fact that A occurs, does not affect the probability of B occurring. So the fact that the first one happened has zero influence on the second one. An example of this would be to toss a coin and roll a die. The outcome on the coin has zero influence on the probability of the die roll. A non-example, examples of something that would not be independent, driving on ice and having an accident. If you know that you're driving on ice, your probability of having an accident does change. It's more dangerous to drive on ice, so you're more likely to have an accident as compared to when you're not driving on ice. So this would be an example of something that's not independent. The first one actually does affect the second one. Now that we have that idea, let's talk about our next rule, known as the multiplication rule. So the multiplication rule looks like this. The probability of A and B both happening is the probability of A times this weird thing that I haven't seen before. And this means the probability of event B given that A has already occurred. So we read this as the probability of B given A. And essentially what it means is we assume that A happened exactly the way we wanted it to, and then determine the probability of B. So let's look at some examples of how to use this. So let's suppose we want to roll two dice. We want to find the probability of getting a 2 on the first die and a 5 on the second die. So here's what our multiplication rule says. The probability of getting a 2 and a 5 is the probability of getting a 2 times the probability of getting a 5 given that we got a 2. So let's start with the first piece, just the probability of rolling a 2 on a die. There are 6 sides of the die with one number 2, so 1/6. For the second piece, essentially we know we rolled a 2 on the first die, so what's the probability of now getting a 5? Well, these events are independent. The fact that we rolled a 2 on the first die has zero influence on the second die, so it would still just be 1/6. So essentially when our events are independent, when the probability of one does not affect the other, this last probability here is really just the probability of event B, the probability of rolling a 5 in this case. Let's look at another example. Let's suppose we draw 2 cards with replacement. So what that means is we draw a card, put it back in the deck, shuffle, and then draw a second card. What is the probability of getting 2 hearts? So I'm going to abbreviate hearts with an H here. The probability of a heart and a heart. We know there are 13 hearts in a deck of cards out of 52 cards. So the first heart that we draw, we have a 13 out of 52 chance. When we go to draw the second heart, there are still 13 hearts in the deck and 52 cards. So we multiply by 13 over 52 again. So we get that the chance of drawing 2 hearts with replacement is 0.0625. Let's look at another example. This time we want to draw 2 cards without replacement. So what's the probability of drawing 2 hearts? So I really only changed one word in this problem. Before we were drawing 2 cards with replacement, now we're drawing without replacement. When we draw the first card, there are 13 hearts out of 52 cards. However, the second card is now different. The fact that we're doing this without replacement means once we draw the first card, we keep it out of the deck. So there's no longer 52 cards, there's 51 cards. In addition, when we do this, we assume the first card was drawn exactly like we wanted it to be. So we're going to assume that that first card was a hearts that was drawn. So now there's no longer 13 hearts in the deck, there's 12 since we've removed one. So we just multiply 13 over 52 times 12 over 51. And that gives us a probability of about 0.0588. Let's do one more example. So out of 8 guinea pigs, we know that 5 are pregnant, and we're going to select 2 at random. So I actually want to find 2 things, the probability that both of them are pregnant and the probability that none of them are pregnant. So let's start with the first one, the fact that both of them are pregnant. So when I pull the first one out, I would have 5 out of 8, since 5 out of 8 are pregnant. We then need to pull the second one out, but we've already removed one of the guinea pigs, so we're down to 7. And we know that that first guinea pig that we removed was pregnant. So we now only have 4 pregnant. So we would have 5 over 8 times 4 over 7. which is about 0.357. Now let's look at the second one, the chance that none are pregnant. So when I draw the first one, we know that if there are 5 pregnant guinea pigs, there are 3 that are not pregnant. So that would be a 3 out of 8 chance that that guinea pig is not pregnant. For the second guinea pig, there's now only 7. And since we had 3 that were not pregnant and we've already removed one of them, we're down to 2 that are not pregnant. So I have 3 over 8 times 2 over 7, which gives me about 0.107 chance that neither one of these guinea pigs is pregnant.